logics. In the previous class, we have discussed about the behavioral model and also discussed about the data flow model, which are called as levels of abstraction. In the today's class, we are going to discuss about the structural model. Okay, this is also levels of abstraction, in which we are going to use these three different styles of levels of abstractions to describe the relationship between the inputs and outputs, okay, in the architecture. Okay, so without any delay, let's go into the video. So before watching this video, I recommend you guys to watch those videos. If you haven't watched those videos, then I recommend you guys to watch those videos and then only return to this video. Then only you can have a continuity in learning, and also you will enjoy to learn. And also if you are not going to watch those videos, then you might get confused, okay, with my discussion. So without any delay, you just watch those videos and come back to this video. If you already watched those videos, then let's move into the video. So structural model, okay, this is also one type of a level of abstraction. Okay, yeah, structural model, which is the third model. We write VHDL program based on the internal structure of the circuit. Okay, based on the internal structure of the circuit, we are going to write the code. Okay, in the architecture, that writing of that code is called as the structural model. Okay, we need to write the individual codes for the all the components in the structure. Okay, for example, we are going to take the full adder, right? See, if you are going to take the full adder, as we already know from the previous videos, I already told many times, the full adder consists of three input ports and two output ports, right? So this full ladder is made up of, as per our digital electronic discussion, this full ladder is made up of two off adders and one OR gate. Okay, as per the digital electronics. Okay, you guys will learn in that, right? This full ladder is made up of two off adders and one OR gate. Again, this particular off adder is made up of one XOR gate and one AND gate. Okay, so the least component, the least possible component that we can able to write code for it is the gates. Okay, using the operators, right? There will be operators like AND, OR, XOR, NAND, and NOR, etc. Okay, those things we are going to discuss in the future video. For now, you just remember that for any digital design, the least possible which is a leaf cell. Okay, we will call it as a leaf cell. Okay, the least possible design that we can able to write in the code format is the gates. Okay, gates are basically 7 types. Those are AND, OR, NOT, NAND, NOR, XOR, XNOR, right? We can able to write codes for those gates. Okay, again these gates are made up of transistor internally, but we can't able to write the code. Okay, it will be very difficult. Okay, there is no any abstraction like that writing code for the transistors. I think it might have, but we shouldn't need to learn that thing. Okay, if you need to learn that thing, you need to have a basics of the analog electronics as well, and analog electronics and EDC as well, so that we are not going to discuss that part. Okay, we are having only 3 levels of abstraction. Those are the behavioral model and the data flow model and the structural model. In the structural model, the least possible or the leaf cell. Okay, leaf cell is nothing but the further we can't able to divide that circuit. Okay, in the sense, further if we divide, then in that for that internal parts we can't able to code. Okay, we can't able to write the code. Okay, that's the point of mind. So the gates can again further divided into transistors, right? But we can't able to write the code for the transistors. That's the point. That's the point of mind. So that we are going to say that gate is a leaf cell. Okay, so that from that we know that full adder requires 2 off adders and one OR gate. Again, this off adder is divided into it will require the one XOR gate and one AND gate. So that what happens is, so we require 2 off adders, right? Then we require 2 XOR gates and 2 AND gates and one OR gate. Now what we are going to do is we are going to write individual codes for the all these 3 types of gates individually, separately, using any abstraction. Okay, you are going to write code for the one XOR gate and one AND gate and one OR gate. Okay, after writing code, you will use these codes to build the half adder, and then the full adder. Okay, this is called the structural model. Okay, when I am going to discuss you with the example, then you can able to learn. Okay, just a second. Yeah, so when I'm going to discuss the example, you will be able to understand very clearly. See, let's discuss the example and write the code. Okay, just a second. Yeah, so I'm going to take the full adder. Okay, this white box is, if you are going to consider this white box as a full adder. Okay, so external view of the full adder is usually external, not only full adder, external view of the any circuit we are going to specify with respect to the entity. Okay, and we also know that from the previous video I have discussed that for any design, okay, for any same design, the entity will be always same. Only the architecture may varies depending upon the levels of abstraction that we are going to use. Okay, okay, it means for full adder, if you are going to write the code in structural model or the data flow model or behavior model, the entity will be always the same, right? That's my point. So that the external view, you can see that we are going to see the outputs, two outputs, those are sum and C out, carry out, and the inputs, if you're going to see that we have three input ports, those are A, B and C. Next, so this full adder is a white color box. In that we can able to see that two half adders are used because as per our digital electronics discussion, we know that full adder is made up of two half adders and one OR gate. You can see there is a one OR gate. In that half adder, okay, I am going to mention half adder, first half adder as half adder 1 and second half adder as half adder 2. Okay, in that first half adder we are having one XOR gate and one AND gate. Similarly in the second half adder we are also able to see that another XOR gate and another AND gate. Okay, internally. So the input, the first input A is going to apply to the first XOR gate is the first half adder, and the second input B is going to apply to the XOR gate second input. Okay, then the resultant will be A XOR B, right? We know that. So we are treating this A XOR B as S1, which is a intermediate signal. Okay, this is an intermediate signal whose value is equal to A XOR B only. Okay, whose value is equal to A XOR B only. This is called as intermediate signal. Okay, it is can't be either input or output because it will be output from the half adder 1 and it will be input to the half adder 2. So we can see that it will be output from the half adder 1 and input to the half adder 2 XOR gate. So we can say that this particular we can't able to say that whether it is either an input or output. We can't able to declare like that. So the intermediate signal is we can't able to judge it, right, whether it is an input or output. There is no mode for it. So next, similarly both the inputs A and B are going to apply to the AND gate and we are getting the output A and B, and this signal is also a intermediate signal which we are going to call it as S2. Okay, this is also an intermediate signal. Yeah, for the second half adder, the S1, which is the output from the XOR gate of half adder 1, is going to apply to the XOR gate of half adder 2, and the third input seed is also going to apply to the second half adder, second half adder XOR gate, second input, and we are getting the output as S1 XOR seed. But what we know from the previously, I have told you, right, S1 is nothing but the A XOR B. It means we are going to get the expression at the end of the second XOR gate in the half adder 2, that is A XOR B XOR seed. This is nothing but our sum expression, right? This is nothing but our sum expression. Okay, so we are not considering any intermediate signal over here. Okay, why? Because this is the value that we require, right? This is the value that we require as an output, so that we simply sending it the output, sending it to the output, and declaring the output port as sum. Okay, next if you are going to see the carry part, carry part. Okay, let me clear everything. Let me discuss about the carry part. Okay, see, for the carry part, you can see that there is a bubble, right? There is a, sorry, the black color dot. There is a black color dot. Okay, it means there is a connection, there is a physical connection between them. If you can see this point, this junction, there is no black dot. It means there is no connection between those two wires. Okay, even though those are passing from one another, there is no connection, physical connection between those two wires. Whenever there is a black dot, we need to treat it as a physical connection between the two wires. Next, okay, for the under, for the sorry for the disturbance, for the under, we are going to apply similarly A and B. Okay, we are going to apply the A and B, and we are going to get the AB. This thing I have already discussed with you, so that we are getting the S2. Okay, we are declaring it as S2, which is a intermediate signal, which can't be either input or output. We can't able to judge it, right? Because it is an output from the off adder one, and it is going to the input. It is going as an input to the, it is going as an input to the OR gate. You can see that OR gate, right? Similarly, the seed is getting applied to the AND gate in the second half adder, and the resulted from the XOR gate one, from the half adder one, which is, I have told you, as a S1 intermediate signal, is also applying from this point. Okay, this point to the AND gate. From this, we are getting the result as seed and with S1, where S1 we already know that S1 is nothing but A XOR B. It means A XOR B within the parenthesis and operation with seed. This thing we are going to treat it as an intermediate signal, which is S3. Why? Because it is not our final expression, right? So I am going to treat it as an S3, and this S3 is getting applied to the second input to the OR gate, whereas the first input to the OR gate is S2. Okay, from this we are going to get the C out, that is AB plus BC in plus C in A. So let me prove that. Okay, from this OR gate we are going to get the one is S3 and also S2, right? S2 OR with S3. Okay, I have wrote here, and C out will be equal to, this value will be equal to, C out will be equal to, C out will be equal to, what is S3? S3 is nothing but C in S1. Okay, C in S1, right? C in S1 plus S2 is nothing but A and B, right? A and B. Okay, A and B. You can see over here A and B, and S3 is seen with seen and with S1, where S1 is nothing but A XOR B. Okay, all these three signals are nothing but the intermediate signals. Okay, all these three are the intermediate signals. Okay, intermediate signals. Intermediate signals. Intermediate is nothing but the in between. Okay, intermediate means in between. Intermediate signals. Okay, signals I am mentioning. Okay, so from this, what we are going to, I am going to substitute the value of S1, that is A XOR B. Okay, A XOR with B plus AB. What is the expression of A XOR B? We know that C will be equal to AB bar plus A bar B. Okay, plus AB. Okay, if you are going to expand this, let me expand this. C Okay, that is C in A B bar, C in A B bar plus C in A bar B, C in A bar B plus AB. Okay, yeah, from the first term and the last term I am going to take common A. Then what happens if I am going to take the common A? Then I have C in plus C in B bar, C in B bar plus B. Okay, C in B bar plus B. Okay, and I am going to write AB two times. Okay, AB two times, AB two times, AB two times. We can write right AB plus AB. It means I am going to tell what I am going to tell is A plus A will be always equal to the A, right? So that I have written AB two times. Okay, so that I have written AB two times. Next, so there is C in A bar B, right? From this I am going to take from these two terms. From these two terms I am going to take B common, and previously I have taken A common from these two terms. Okay, so I am going to take B common, and then what happens? B common. What happens? C in A bar, right? C in A bar plus C in A bar plus A. Okay, from the absorption theorem we know that, so from the absorption theorem we know that A plus A bar B will be equal to A plus B. Okay, this point we should know from the absorption theorem. Okay, from the absorption theorem we should remember this point. How does this came means A plus A bar, this becomes, this particular thing will becomes A plus A bar into A plus B as per the distribution theorem. It means A plus A bar will be, this value will be 1 dot with A, anything will be the anything value. It means 1 dot A will be A, right? So that we got the A plus B. Okay, see, this thing is called as the absorption theorem. As per that we can able to say that C in B bar plus B will be B plus C in. Okay, then it will become A C in plus B. Okay, whereas similarly C in A bar plus A will become A plus C in, then it will become, in between there is plus. Okay, in between there is plus, C there is plus B into C in let me C in A bar, C in plus A, right? C in plus A. So let me erase this thing, this part, just a second. Okay, if I am going to erase this part, okay, you just multiply A with C in, then it will be A C in plus AB. Okay, plus AB plus, again you multiply B with C in, it will be B C in plus AB, right? Plus AB. AB plus AB will be AB, right? AB plus AB will be AB, right? Because A plus A will be always A, right? Then BC in BC in plus AC in. Okay, so we got the expression, right? We got the expression of the carry. This is the expression of the carry, you can see over here. Okay, we got the expression of the carry. Okay, this way we got the expression of the carry. Previously I have told you, right, how we got this sum expression, because there is s1. S1 is nothing but the ax or b. Ax or b. x1 is nothing but ax or b, and we have ced here. Okay, ax or b, x or ced. So for sum there is no any problem. Okay, easily we can able to say for how does the carry came. For that we need to see like this analysis. So this is all, everything will be discussed in the digital electronics itself, but if anyone doesn't know, I told you this part. Okay, so there are two XOR gates and two AND gates and one OR gate. Okay, why? Because there are two half adders. In each half adder we are having one XOR gate and one AND gate. It means there are two half adders, then we can able to say that there are two XOR gates and two AND gates, and there is one OR gate, right? So in total what we are having leaf cells are XOR gate and AND gate and OR gate. We are having three leaf cells, those are XOR gate, AND gate and OR gate. Yes. So we are going to write individual codes for this all these three gates. So I'm going to write individual codes for all the three gates. First for the XOR gate. XOR gate inputs are the A and B. Input ports are the A and B, whereas the output ports are the Y. Okay. Code. Similarly, I'm taking entity. XOR gate is also a keyword. Okay. XOR gate is the name of the entity, and we are declaring the port class because we doesn't require any generic construct, right? So that we are proceeding with the port class. There are two input ports. Those are same as the those are both are input ports, so that we are going to use them with separator comma a comma b colon in std logic. Std logic is of type, okay, type of the ab, and you can also use here, you can also use bit. Okay, here you can also use the bit, there is no any problem. And we have the output y, and it is the type of out, and std logic, and after this parenthesis only we are going to mention the semicolon over here, and we are ending the entity with the entity name, which is XOR gate, XOR underscore gate, and we are starting the architecture behavioral, which is the architecture name. It is also predefined. It's not predefined, it's a user defined of is a keyword, and XOR gate, which is the entity name. This entity name we need to specify. Why? Because we are going to write the code architecture for the entity, right? The architecture is always followed by the entity. So after we are going to mention is and begin. Okay, we are going to begin because there is no any intermediate signals in between the XOR gate, right? In this XOR gate there is no any intermediate signals, so that we are beginning the code. Y less than or equal to, less than or equal is a assignment operator. A XOR b, XOR is a operator, right? It is a keyword. Semicolon after we are ending the architecture which we have started, and we are mentioning the architecture name behavioral, semicolon. We are ending the with the semicolon. Similarly, we have written code for the AND gate. Similarly, AND gate also require two inputs ports and one output port y. Same, both are same. We have written the name as AND gate, and both inputs are same, and output is also same. And AND gate entity we have entered, and same we have mentioned the AND gate entity over here. Whereas in the logic we are mentioning the just simply we are mentioning the AND operator. Okay, you just see this code, you will able to understand. If you understand this code, then you can able to understand this code as well. Next, similarly the OR gate. OR gate also is same. We are having two input ports and one output port, and sorry, and we are having the entity, and I mentioned the OR gate as a entity name. Same inputs, right? Same input and output also same, and we are handed the entity. And architecture behavioral we started, and also we mentioned the this entity name here, and we are going to simply use the OR operator. In the previous class we have used AND and XOR. In this case we have used the OR operator. Okay, yeah. Next, using all those three, we have what we have done till now is we have written the individual code for the gates. Now what we are going to do is, using those individual codes, we are going to build a full adder. Let's see, full adder. This is the full adder, right? Okay, I told you, right, there is an intermediate signals. Those are S1, S2 and S3, where we need to specify these intermediate signals. Okay, in the architecture, after giving the name for the architecture, before they begin, in between those two lines, we need to declare these intermediate signals. Those are S1, S2, S3. We require three intermediate signals, right? Yeah. Next, let me tell you, code for full adder in structural mode. Yeah, this is the block which I have minimized. Okay, for our reference, I have minimized. Next, we are specifying the entity, and the entity name is FK, and easy is also keyword. I forgot to mention it. And port, we are writing the port class because we doesn't require any generic constants. Port, and the inputs are the three input ports. You can see over here, inputs are three input ports, A, B and C in, and I am imagining them as in and STD logic, and some comma C out. Those are the outputs. Okay, two outputs you can see over here. We are having two outputs. I mentioned them over here, and out STD logic. I'm ending the entity that I have started with the entity name, which is FK, and starting the architecture. Okay, this is the most important point. Okay, architecture, which is the I am writing the structural model, so that I have given name as structural. It is not a predefined; it's a user defined. Of is a keyword, and FA is the entity name. For this entity only, we are going to write the full adder, right? We are going to write the code, right? So that I have mentioned FA, and is also keyword. So in this we require three intermediate signals, S1, S2 and S3, right? So I'm going to specify them as signal. Signal is a keyword, S1 comma S2 comma S3 colon STD logic. So we shouldn't mention any input and output. That is why, because we can't able to say intermediate signals as we can't able to decide completely. We can't able to decide whether the intermediate signals are inputs or outputs. Why? Because this S1 is output from the half adder one, and also similarly this S1 is only the is also the input to the half adder 2. It is intermediate. Okay, so that we can't able to decide whether the S1 is input or output. So there is no mode for the intermediate signals. That point you need to remember. Next, we are going to use those designs which we have used in the which we are used in the which we are used in the this particular half adder full adder. We have written already codes for the XOR gate, AND gate and OR gate, right? We need to call them into this code. For that we need to use component. Okay, component we need to use, and component XOR gate. Okay, XOR gate, you need to use this name. Okay, you need to use this name only. Why? Because in the previous slide I have used XOR gate. For XOR gate I have used XOR underscore gate, so that this particular name only you need to use in the code, in this code. Okay, in this code you need to use this particular name only. Okay, in this code you need to use this particular XOR gate only. Is, okay, is a keyword. Again, port, we are going to mention A comma B. These are your wish. These are your wish. A comma B colon in STD logic, Y colon out STD logic, and we are going to end the component and you need to mention the name XOR gate. This is optional. Okay, this is optional whether you mention the XOR gate name or not. This is optional. If if there is no this as well, then also it will work. Okay, we just put the semicolon over here. Okay, next we are calling the second AND gate. Okay, we are instantiating. This is called as component instantiation. Okay, component AND gate, similarly AND gate. Similarly we are mentioned the port. Okay, A comma B and we have ended the component. Again there is another component left, which is the OR gate. Component OR gate is port A comma B in STD logic, Y out STD logic and component OR gate. Okay, all these three are the component instantiation. Why only three? Because this particular full adder needs only three leaf cells. Those are the XOR gate, AND gate, and OR gate. Okay, yeah, and I also mentioned the signal declaration. Okay, intermediate signal declaration. Okay, next. Now we are going to write our logic. Where we are going to write our logic? I have told you, right? After begin, you need to write the logic, so that I am beginning the code. Okay, before that, let me tell you this term. Use signal before begin to declare the intermediate signals, right? We have used it before begin only, right? Before begin, after the declaring of the architecture name. Yeah, and those are access both input and output, because these particular intermediate signals will be access both input and output, so we don't specify it as an input or output. Okay, use component and declare all components used in structure. Okay, what are the components that we are going to use in this structure are, yeah, XOR gate, AND gate, and OR gate. We have mentioned them in the code, right, using the component. Okay, this is called the component instantiation. Now in the begin, we are going to use port map in the begin to make the structure using the component. These particular components we are going to use. For this, we have written code in the previous slides, right? We are called those codes into this full adder code by using the concept called component instantiation. Now we are going to use these components in the begin of the architecture to specify the logic of the full adder using the structure. Okay, yeah, with the help of the port map. So begin, continuation for this code. Okay, for continuation for this code, begin, we are going to use a label. This is user defined XOR1. Okay, this gate, for this gate we are going to write the code XOR1, XOR gate, XOR underscore gate. XOR underscore gate is nothing but this particular name. See, let me change the pen. Oh yeah, this name. Okay, why we are going to use only this name means, because in the entity we have given XOR underscore gate only, so that you need to use this name only. Okay, and then port map. Okay, port map, what are the inputs to the XOR gate? 1, A and B. So the in the parenthesis A comma B, and then what is the output as per the circuit? It is S1, which is an intermediate signal, right, which we have already declared, right? And S1, bracket close and semicolon. Similarly, label 2, which is the XOR gate 2, it means this gate. XOR gate 2 means this gate. Okay, XOR gate 2. What are the inputs to the XOR gate 2? XOR gate port map. Okay, same you need to use. XOR gate. Okay, you can use how many times you required. Okay, this particular XOR gate you can use infinite number of times after you are mentioning it in the component instantiation. Same XOR gate you can able to use in infinite number of times. You can able to instantiate. Okay, you can able to port map in the begin block, so that we are going to use the same. Then what's the difference? Because the difference will be in the port map. Okay, in the port map, what are the inputs and outputs you are going to specify, that will show you the difference. Okay, so in the previously we have mentioned A comma B comma C S1, because for XOR gate 1, those are the inputs and the outputs. For the XOR gate 2, the input, the first one input will be S1, and the second input will be Cin from the Cin. Okay, and also we are getting output as sum, right? We are getting the output as sum. Yeah, similarly the next gate is AND gate. Okay, we have mentioned the AND 1. Okay, AND 1 as a label, colon. So AND gate, we have AND underscore we have used it because we have given AND underscore gate for the entity port map. What are the inputs for the first AND gate? This is the first AND gate, right? One is A and B, and we are getting the output as S2. Okay, we are getting the output as A and B, but we are declared this. We want to declare this particular A and B as an intermediate signal. Because why we need to declare this signal as an intermediate signal? Because this is not the final carry expression, right? This is the carry expression from the half adder 1. Okay, so we shouldn't need this value. we need the carry expression from the full adder, so that we are declaring it as an intermediate signal with the help of the S2 signal, okay, which we have already mentioned in the signal declaration. Next, N2, okay, this is N2, sorry, printing mistake, this is N2, okay, this is N2, just a second, okay, this is N2, right, this is N2. Next, R1, okay, R1 means this gate, R1 means this gate, R1 OR gate, R underscore gate. Why? Because we are going to use, we have used R underscore gate as our entity name, okay. Port map, what are the inputs going to the R gate or the S3? One is S3 and another is S2. The position you can change, okay, you can change the position as you like, okay. This particular position depends upon the uh, in the entity how we are going to declare, okay. In the entity, first we have mentioned the a comma b colon in std logic, and then output, right. First we have mentioned two inputs and then output, so that it will take it as like that only. It means it will what are you going to specify in this? First, if you are going to specify in the entity, if you have specified inputs, then the first two will be treated as an inputs only, and the last one will be treated as an output. If you have specified in the entity first input as an output, then the first input, the first value that you are going to mention in the port map will be treated as an output. Okay, this point you need to remember. Okay, yeah, we will discuss again further. Okay, don't worry. So S2, S3, and we are getting the output final carry, which is C out. Okay, we are getting the output final carry C out, and structural. Okay, we have begun the architecture. We are going to end the end structural. Okay, what I have told you is, see, I will tell you. Okay, in this port, in the entity port class, first you have mentioned inputs a comma b, and then output, so that when you are going to use the port map, it expects you from it will expect you to mention three values, two inputs and one output, in the same order, okay, in the same order how you have mentioned in the port class, which is written in the entity, okay. In the port class we have mentioned firstly both the inputs and then output, right. Similarly, when you are going to uh, give the values in the port map, you need to give in the same order, okay. Then only it will give you the correct functionality, okay. This point you need to remember. Otherwise, there is also another method, okay, that I will discuss it in the coming videos, don't worry. And this is known as component instantiation, and this is also known as component instantiation, and this is also known as component instantiation, and this is the signal declaration, okay. That's it for the video. So if you like the video, like, share and comment or subscribe. Thank you.